So can anyone hear me?
Yes, Ajahn.
Okay, thanks.
Recording in progress.
So I think maybe today is the last discussions on the optimization, right?
Ajahn,
Yes.
I have a question about beta 1 and beta 2. I see your answer on the line, but I quite confused. We don't have it. We cannot draw the line or curve because we have many unknown. It1, it2, and it3 example. So why we can imply one and beta 2 if delta b is greater than more greater, and we can infer delta f is greater. Can you
and also clearly understand what the question is, but you're talking about the beta 1 and beta 2, right? The same thing that you have asked in the live group.
Yeah.
Okay. May I address about this question later? I try to complete the discussion first, okay, today, and after that we can have the time for discuss any problem.
Yeah.
Okay. So I think, let me try to, because today I will need to use the MATLAB to facilitate you somehow to make you feel comfortable with this computation tools. I don't know how much you're familiar with the MATLAB software, but I think it's quite easy to use, and maybe today I will be able to show you some of the applications, especially for the optimization. It's make you might feel very easy when you use the MATLAB. It's very helpful and can help you a lot of mathematical work. Okay, maybe I change the desktop to another PC so that I can use the MATLAB. That's my tablet. They don't have the MATLAB install. Let me try to share with another account. Okay. You start to numerical searching, right? Yeah, I can share the screen here. Yeah. So maybe today I would like to discuss about the numerical searching techniques using for the optimization. As you see in the first paragraph of the content, saying that we often encounter the optimization of a complex problem in the real world. They contain many variables and sometimes many constraints, especially for our structural design, structural analysis. Many cases we found in most of our applications, they are not only one, not only two, three variables. You are talking about maybe 100 variables. For example, if you want to design a tall building, the structure where you have at least 30, 40 stories, and in each story you might have saying like 30, 40 is again number of columns. So in total, you have each node of the columns top and the bottom of the columns, you better have the known of our structural problems. Therefore, in total, you might talking about 1,000 variables that you are searching for the optimization when you try to design your building with the objective. So using the calculation that we have discussed so far, based on the Hessians, the borderless Hessian, the Lagrangians, it look good. For a number of variables, not so much. But when your problem has a lot of variables, no doubt you need maybe numerical techniques to help you to get the solution. And one of the helpful topic, I think, are using the numerical techniques that we are going to discuss today. It seems I lost the connection, right? Can you hear me?
Yeah.
Hello? Can anyone hear? Sorry, there's my internet is not so good. Let me do it again. It's not sharing. Okay. So today that I would like to discuss is about the searching technique. The idea is very simple. Let me do it very brief on this slide. Like imagine if you stand on the mountain and you are trying to go to the, how do you say, the deep valley, right? The minimum point, the deep point. So you have to go down from the mountain. How you go to the deepest locations? The idea is very simple. The first, you need to find the directions, find the best directions. And then the next step is, once you obtain the best direction, you have to go with the appropriate, how to say, the best distance. How much you, how far you have to go in along that direction. And after you go to a proper location, you will find the next step by, again, finding the best directions. And then go to the, how far is go, like the best distance. Okay, so it looks like find the direction, then the distance. When you go to the next position or next location, again, find this direction and the distance. After you go to the next locations or position, you find the next direction and locations. That's it. It's like that. So to show you some of that, what do you say, applications, I use a very simple multiple variable search technique and discuss with you. Here you can see the univariate search method. And in this search method, the idea is is like just very simple as I have to go, if your problem contain, for example, x1, x2 until xn, what I have to do is I will define my base direction along x1 first, and then I go along x2, and then I go along x3, and then I go along x4 until xn. And if the location I obtain is not good enough, I will go starting from direction x1 again, following with x2, x3, x4 until xn. This is the second law. Okay, keep doing like this until you achieve the position or the location you think is the minimum. So the algorithm you see is just one of the drawback of the searching technique is you have to have the starting point. You have to initialize x1, number one. I mean the first location at the starting point. With numerical, no doubt, you need this as the starting location or the point you use to start your searching. And set k equal to 1, and maybe you set the tolerance epsilon greater than something like a 0.0001, whatever you can accept for the allowance for your solution optimization. If you think the difference of just 0.001% or 0.001 is okay for you, so you set the tolerance like that. It depends on the problem you are looking, you're searching, right? The second step is to optimize the function, objective function f, along the alpha k. Alpha k is the direction k and the distance alpha. Okay, and it can be written as the f of xk plus the alpha ek, where ek is just the unit direction, unit vector along the direction k, and the alpha you see just a constant. Is the constant along that direction, direction of ek. And following for k equal to 1, then 2, 3, 4 until n, and do check the alpha k at the last step. Check whether it's smaller than epsilon or not. And if it's smaller than epsilon, it seems that you accept this as your, how to say, your optimization, your minimum or your maximum, and then you stop. Otherwise, you repeat again and again for the searching. Okay. Now I think it's an example talking about the, I think this is a convex function. 3x1 squared plus 4x2 squared minus 5x1 x2 minus 2x1. This is the kind of a surface, right? Contain only two variables. And I will use the univariant to solve this problem using numerically searching based on the univariant searching algorithms. And I will start with the location 5, 5, x1 equal to 5 and x2 equal to 5. This is my x sub 1, is the k equal to 1, right? Is the first location. And I will keep searching until I achieve the minimum point. To show you this, maybe it's better to explain through the MATLAB. Let me try using the MATLAB here. Before using the MATLAB, maybe I need the math work. Okay, this is your privilege with Chulalongkorn University, especially our faculty, engineering faculty. We subscribe this software, the MATLAB, you see this is my account. And I believe that as long as you have your student email, I think you can install the MATLAB, the licensed MATLAB fully option. I think if one of you can find a way to, how to say, connect with the computer center of our faculty, it's better. I think it has a Facebook or the website to explain how to use the student ID and your email all together to install the MATLAB. There's the guiding. Okay, so I expect that it's not so difficult for all of you to get the MATLAB because we have subscription from the MathWorks already for all of you. We have, I think in total, maybe 1,000 or 2,000 license. I believe that is not a problem of your installation. So if you install the MATLAB, I believe, let me try. This is a MATLAB. I just installed this. Okay. Once I open the MATLAB, after my complete the installations, it would something like this, right? You see in this slide, like I contain the command window. This is a command window, and I have the folder where is the active part of my MATLAB programs. This is about the detail. If I click on the file, it could provide me the detail. It's no detail available, no problem. And this on the right-hand side, you see this is what called the workspace. For example, if I type something like A equal to magic 3, magic 5 there. Okay. On the workspace, you can see there's a matrix A now. It's a 5 by 5. It's a double precision. So even though you show in the output A equal to 17, 24, 1, 8, 15, something like this, is no doubt inside 15 is 15.000 is the double precision. So this one is very accurate using the MATLAB. This magic matrix is just a matrix that I think is you see in every direction, in every row, in every column, the summation is the 65. You see, if you do the summation of 17 plus the 23 plus 4 plus 10 and plus 11, you got the 65. And the second column as well is 65. Third column, fourth, the fifth is all equal. And you look in this one, it just it's kind of magic, right? You put the number from 1 to 25 in each location. And I believe the summation in the low is A transport. If I do like this, A prime is A transport. You got the same thing, 65. That's why they call the magic. In the summation in any directions are the same or equal. Okay, and if I want to find the eigenvalue, you know about the eigenvalue, right? I just type EIG of A, press enter, and I obtain all the eigenvalue, 5 of them. And if you want to find also the this just the eigenvalue, right? If I want the eigenvector as well, what should I do? I think it should be something like a V and D. If I put the vector as well, it could be something like this. Yeah. You see, I have a eigenvector for each corresponding eigenvalue. And I don't know whether Dr. Chatpan already discussed a bit about the MATLAB with you or not, but I think it's not so difficult for you to learn from the getting started manuals or the guideline or the YouTube, Google. There's a lot of very good documentations about how to use the MATLAB. It's quite easy. Okay, let me go back to our subject where we want to find the minimum of this function, right? 3x1 squared, 3x1, 4, 5, 2. Okay, let me try this. F. So F is the function. I'm not so sure about the X and Y. I believe it's something like x 3x squared. I just type 3 multiply with x squared is the power 2. I use x1 by variable x, and x2 maybe I use y for my variable. So it's maybe not so confused. But actually you can use x number 1 and x number 2 in the MATLAB. It's easy, but for how to say a simple typing, right? I want to be x and y, maybe plus, I forgot. Let me forget about 3 part 4 minus 5 minus 2. 3 part 4, I'm sorry. Minus 5. I'm sorry. X, Y, minus 4, right? Oh, minus, forgot again. Minus 2x1. 2x1. x1 is my x. It should be okay. I'm sorry. Okay. This is, I define the functions of mine. Is the function contain x and y, and x here in the MATLAB, my MATLAB that I'm typing to show you is it's just x number 1 in our example, and x number 2 I replace it by y. Okay, so if I want to plot what I call the surface, it's just the f surface of my function f. It will pop up the surface for me. You see this example, the surface is like this. It's a kind of I think you see it's a convex function, I believe, but it's not easy to see the bottom. I mean, what is the deepest or the minimum locations. However, I think we will find this one. Go back to the first one. From the example, I do believe that I will show you that I will start from x1 equal to 5, 5. When I say x1 equal to 5, 5 mean what? Mean I will start from this location because I don't know where to start. I just select 5, 5 for you. Maybe here. You see, x equal to 5, y equal to 5, and z is the objective function, right? So the function f is equal to 40. If I move to here, I think the minimum is location. Maybe my feeling is loudest. You see, z or the objective function from 40 reduced to 6.7. So it's close to minimum, right? It's better than 5, 5. Maybe I have to go to 2 point something of x and 2 point something of y. But never mind, let me do with the first idea, univariant, but I call it univariant. The univariant is the thing that we will go in x direction first and then along y directions. X direction, I think I believe is like this. I go from that to that, right? X, this is, you see x change from 5 to 3.5. Or if you go to here is the x equal to x1 is equal to 2.0, something like this from the beginning of 5.5. So the idea, you see, it just, we are, I can draw the curve for you. It could be like this. You go along this direction, right? This is, in our example is x1 direction. We will go along x1 direction. We not go here. We will not go directly to the optimum point. I believe optimum point is over there, right? Look from the surface. What? Assume you cannot plot this when you have many variables. So the idea of univariant is to go along each direction. X1 first, follow with X2, and then X3, and then X4, something like this. So that's why I think what we have to do if we're using the univariant, we have to go first along X1 direction. Assume that if we go along X1 direction, we stop here. Assume that we stop here. The next step, we have to go along the X2 direction. From there to here, maybe we stop to the optimum point there. And if you don't feel it's close to the optimum yet, you have to go along X1 again, right? In this direction. Maybe we stop there and then we go along X2 direction. We stop here like this. You have to go like a zigzag. X1, X2, X1, X2. For this example, it could be something like this, okay? I'm sorry. So hope you understand. By the way, using the MATLAB, maybe I will show you just one click, you got the solution. Later I will show you, but let me start with just the standard algorithm like univariant, the Povo, steeper descent, something like this first, okay? There might be one function as well. I think it's called the surface, contour, not the surface. F contour. I want to show you the contour plot of this function f. Just type f contour of f, and I think I got the contour of something like this. You see 5.5 is here, right? Let me do the grid line for you. I type grid, mean I need the grid line to turn on the grid line for the plot. Something like this. Okay, 5.5 is over there, right? Is this location, and maybe we have to go along the X1 first and then the X2, but the optimum point is close to here. This is just a contour plot. And if you want me to zoom in, it's quite easy by looking at this. I will find the optimum point U by just plotting the contour. It's not. Oh, it's very difficult now to see, but it's something like, I think X1 could be something like a 0.6 something, and X2 could be 0.4 something, close to here. Could be the optimum solution. Okay, let me turn back. Why is it going display? Okay, so this is a surface, and I think The first location will start with 5, 5, maybe there. Okay. Go back to the handout. You see, I will set myself 5, 5 at the starting point. K set equal to 1, epsilon is 0.1 in this example. The first, I will go along the x1 direction. You see in the f of alpha 1, you can be written as f of x number 1, x location 1 plus alpha 1 e1. Look at the e1. E1 is what? E1 is just direction of the direction along only x1 direction, right? Since you see x number 2 is at 0. So no matter alpha 1 is, alpha 1 can be any real number. So when you multiply alpha 1 with a vector 1, 0, the effect on the 5, 5 location is you go just along x1 direction. And you can see, you see only x1 direction will be disturbed by 5 plus alpha 1, but along x2 direction, just the same. I start with 5 and it will be remain 5 after I complete this step. No effect on the x number 2, right? Only x1 will be affected. This is the way that univariant offer. We go along x1 direction first. And if I introduce this x1 equal to 5 plus alpha 1, x2 equal to 5 into the equation f, you see you introduce this in the f function, the objective function, you can replace everything. I mean, x1 and x2 by alpha 1, right? So the variable is alpha 1. Alpha 1 is what? Alpha 1 is just the distance. Distance. How far you will go along the x direction from the present position 5, 5. This explained by alpha 1 to the optimum locations. And if I replace this alpha 1 into or introduce into the objective function f of x, you see I will have as in equation number 1 here, right? And you see only the alpha 1 is the unknown of mine. So I will try to find what they call the necessary condition. I perform the first derivative on alpha 1 of the f on with respect to alpha 1. I obtain 6 of the 5 plus alpha 1 minus 27 equal to 0. And I can obtain alpha 1 equal to minus 0.5 as in equation 2. And if you want to go along x1 direction, the idea using the optimization, the necessary condition telling you that you have to go back to the origin along the x1 direction with 0.5 distance unit. Okay, you have to go back to the origin with the 0.5 along x1 direction. If you want to make sure that the direction you go and the distance you achieve will return you the real, I mean the minimum, you have to perform the double prime, right? This is about the sufficient condition. You have to perform the f double prime on equation number 2, and you see is equal to 6, right? You perform this is 6, and it's plus the positive number 6. Therefore, it's greater than 0, and it's returned as the minimum. Guarantee the minimum. So it's good to go with this alpha. After you check the double prime, you make sure yourself that if you go to the next position with this alpha 1, you will have smaller objective function. You can smaller the objective function. Okay, so I'm sorry. Let me go to the next. So the next location become, as you can see in this slide, is 0.5 and 5. After the first step complete, you will move to the next position, X, big X number 2. Let me say big X number 2 is the second step of optimization of this univariate algorithm. It's a 4.5 and 5. Okay, let me confirm you from the surface plot. Let me go back to the MATLAB. It looks like if I would like to go along the X1 direction from this line, right? The base location is not here, of course. This one is very high. So the base location along this direction, I believe it's close to here, right? As my visual can tell me like this. Let me to 4.5. If I go to this next grid line is okay, 4.7. You see from 40, the objective function from 40 now reduced to 39.3. It's good, right? Smaller. If I go one step here, oh, it's better. 39.27 is a 4.4, and I believe this one become higher. This one 39.6.7, so it's not good. 4.1 is too high. Let me go back. So I believe, oh, I cannot go there. Let me move to, sorry. I have to refresh. Why is okay, so I believe it's like this. Now you cross to the 4.5, but in this grid line, I just obtained 4.4, right? It's not 4.5, but it's quite different. I think 4.5 is a little bit better, right? But I cannot click for you. Okay, assume this is 4.5. X2 is 5. What I have to do next is go along this direction, right? Along X2 direction. And I believe if I go along X2 direction, let me move this a little bit. It's better to see here, right? Maybe previous is better. I have to go from here, maybe allow there and stop, because that will provide me a better optimum point than existing one along X2 direction. Let's compute where is the base position. This is about the second step. K is equal to 2 now. And you see, we will go along X2 direction. This is what shown in here. You see, this X number 2 set equal to 1 and X number 1 set to be 0. And you see, it will affect only the X number 2, not X number 1. X number 1 is keep equal to 4.5, but X number 2 will be modified by alpha 2. What would be the best alpha 2? This is the equation, right? And you have learned about, this is just the line searching, only one variable, so it's easy. You perform the first derivative and set it equal to 0. This is called necessary condition, right? Introduce this to the objective function. And you will obtain, as in equation number 3 now, that the alpha 2 need to be minus 2.1725. This is the best locations. And the X, big X number 3, the next location is shown in equation number 4. That is 4.5 and 2.8125. Okay, after you introduce the obtain alpha 2 back into the function, you obtain the new position. So you see from X number 2, 4.5, 5, you have to go to X number T here, 4.5, 2.8. 2.8. Let me go back again to the surface and looking the value of 2.8. Oh. Linsa. .8, which means maybe we are 2.8 maybe there. No, it's the 3 point something, right? You see, Z is 20 smaller. Oh, 19 smaller, 19.2, 2.8, maybe there. Okay, 19.2, and if I go further, 19.8 is kind of climbing to the mountain again, right? So it's close to here. Yeah, it's in between these two. But you see, the objective function is smaller and smaller, keep smaller. Okay, and I believe the idea like this, if you agree to accept this position as your solution, you just stop. But if you think it still be able to achieve better minimum point than this, than 19.0, right? The value objective function can be smaller than this. You go further. The next step, if you decide to go further, is to go along again x1 direction, because you have only x1 and x2, right? Along x1, along x2, and then along x1, x2, x1, x2 like this. So I have to go from here, maybe there. I don't know. Maybe this point is smaller. You see, 13 is smaller, right? 10 is smaller, good. 8, smaller and smaller. No, close to there. Maybe around here. 2.x1 maybe close to 2 point something. Okay, but never mind. We will do it by the univariant. That is about the number 3. We will keep going further. Maybe I quiz you on this. Let you try to understand. This is my questions. I prepared this for you. I would like you to calculate the big X number 4 for me. What would be the next position after I obtain this already, right? Remember now, I have this in my hand, but I would like to get a better position. And I show you on the surface already, maybe X1 need to be smaller than 4.5, maybe 2 something, or maybe close to 3 or 2 point something. Okay, let's try to find that. Okay, we go along x1 direction, you see here, only x1. Any questions?
Could I have a question?
Yeah.
If at the first step, we go the direction along the x1, but the second step, why we continue go along x2, at the x2 we go along direction x1 too.
Your question is why we need to go along x1 again, something like this?
Yeah.
Because we already complete x1 in the first step. Is that correct? I am not so sure. I could not catch your question well.
Yeah,
am I correct? Am I?
Yeah.
If that is the question, You see, you go along x1 direction. I show you on the surface, you see.
Yeah.
Even though at the first step you go along the x1 direction, but that is not the solution, right?
Yeah.
I'm sorry.
But the step I will continue go to along each one direction too. Total. And the step 3 we go along each two direction.
No. The first step we go along x1 direction. The
Yeah.
second step I go along x2 direction. The third step I go along x1 direction.
Yeah.
Because we have only two x1 and x2, right? We have only two unknown. But if you have 3 unknown, 4 unknown, you have to complete every unknown first. And then you will repeat with x1 again. Do you understand? For example, if you have x3, you mean x1, x2, and x3 as your unknown, your problem contains 3 variables. The first step, you have to go along x1. The second step, you go along x2. The third step, you go along x3. The fourth step, you go along x1. The fifth step, you go along x2. Understand?
Yeah.
Okay. So let me go back then to the question that I'm going to quiz you. So this problem contains only 2 variables. So the first step, you go along x1 is complete. The second step, you go along x2, and we already complete. And that's why we obtain 4.5, 2.8125 as the new position, right? New base position. We would like to go further. We would like to obtain better solution than this. So we decide to go to the second round. This is the third step, and we go back. I mean, we come back to the first direction. That is x1 direction. That's why you see in this handout, you have here, right? In alpha 3, you have only 1 and 0 as the direction defined. This is mean I go along x1 direction only. I don't care about direction x2. Only x1 direction will be considered here in this step. And you see this is the value of the x1 of mine, and this is the value of x2 of mine here. And I believe if you introduce this one to the f function, f of x, that have the x1 and x2 inside, you will have the objective function now contain only alpha 3 as the unknown. And you can perform derivative, right? To obtain what would be the optimum alpha 3. That is the distance, the optimum distance to go along the alpha 3. And I would like to ask you now, what would be the big X number 4 equal to what? Okay, you have maybe, this is the fourth step, the third step, right? Is a new position. I would like to have the new position. From this one, maybe I will obtain another position better than X number 3 is the X number 4. And I will let you know what is the location of big X number 4. Please tell me and answer me. You have 5 minutes, okay? I will send you the link of the Padlet for you. Yeah, I already did. I already have the Padlet. Share the link. There's my chat. Okay. I think I already sent off you the Padlet link. Don't forget to first write down your ID, right? And then following with the x1 equal to this amount, x2 equal to that amount. And I believe x2 is not disturbed. So it could be something like a 2.8125, right? It could not change. Only x1 actually is affected by this step of analysis, of searching. Okay, within 5 minutes, I think it's not so difficult. And I expect alpha, number 3, could be the negative number, because I show you already the surface, right? You have to go in this close to origin to get a more optimum point. If someone calculate alpha 3 and get the positive number, just say goodbye, right? It's not correct, I'm sure. Okay. Some of your friends already send the solution, you see, very fast. So I have to close first. Okay, let me stop sharing first because I would like to see your answer. Good. Quite good. I got 3 from you, 3 solutions from your classmate, and it's look quite good. I got 10 solution now, 10 from you. Hurry up.
Ajahn?
Yeah.
The answer is 4 only.
Pardon?
The answer is 4 only, right?
The answer what?
The answer what I have to write here is 4.
I have the example for you, right? You look at the Padlet. You just tell me x1 equal to which number, And x2 equal to 2.8125. I'm sure it doesn't change, right? This is a new position.
Yeah.
Okay.
Ajahn, I could not open MATLAB and I sent the answer on the chat in private mode. Could you see
Why
my
not?
answer?
I
don't know.
You don't need the MATLAB. You just calculate by your hand calculation.
No,
send me back the Padlet.
I mean, I send in Padlet, but it not work. So I send the answer on the chat window in private mode. I send to it.
No, I need the Padlet, right? Can you send to the Padlet, because I will save on the Padlet. If you send this chat, you will not have the score.
Oh yeah, let me see. Let me try again.
Yeah, you need to.
Sorry, but my Padlet is not work. Do not work.
Just try, because your friend already sent me maybe 20 of them. So it shows that everyone connect to the Padlet without any difficulty. You just double click on the Padlet, right? The link I sent to you. And type the solution. That's it. Very easy. Okay, one more minute. I already got 21 answers from you. Okay, so if someone still not yet send the solution, please hurry up. Okay, 20 seconds. Okay, time stop. So I will close the link. Okay. It looks quite good, right? Many of you answered I think it's correct. 2.6 something could be the correct one, right? Alpha is minus 1.8. Okay, but some of you say x1 equal to 1.8. I don't think this is a good answer. This is maybe the alpha one. Alpha 3, right? You have to introduce to the previous x, subtract with the alpha 3 first, and you obtain 2.6 like your friend have. Okay, it's quite good. So let me go back to our chapter again. You see, you just keep going like this. you obtain the new position, x number 4, right? And if you ask yourself that this is acceptable to you or not, the objective function is smaller now, is still good for you yet? If you say, oh, it's not yet, you have to go further. What you have to do is to go along x2 direction. The next step is go along x2 direction. And then again, x1 direction, x2 direction, x1 direction, like this. It's quite straightforward. It's very simple. But this is the idea of the first univariant. The next is, I don't think this is a Powell search. The Powell searching method is try to improve the univariant method by employ what they call the acceleration step. The acceleration step is nothing. It's just something like before. Okay, let me draw you this. Okay. With the univariant, what I have do with the univariant is go along x1 direction. This is first, right? And then you go along x2 direction. Maybe here, this is second. And then you go along x1 directions again. This is maybe number 3. And if you don't believe this is the optimum yet, you go further to number 4. It go like this. This is univariant. But the idea of the Powell is do quite different. Maybe I use the red line. I go along x1, I go along x2. The Powell say, okay, if you go along x1 and x2, it means you complete the 2 variable already. Why don't you go back to x1 again? It's not a good idea. Why don't you do this? You see, from the origin, you go along x1 and x2, they draw the direction, the new direction. This is the acceleration step. This is the direction that they think is better. So they don't do the third step with the green. They do the third step with the red. Maybe from number 2, they go to the third step to here. So number 3 of the Powell is like this. Okay. They go in the, how to say, both x1 and x2. Using the acceleration step means you affect both x1 and x2 variable directions. Okay, it's good than just force yourself to go only one direction like a x1 or x2 like that. Is too slow. The Powell belief doing the acceleration means you go to the optimum faster than univariant. Okay, so the first, the second, the same, but the third, they implement the acceleration step. And after you complete the third like this, I believe the Powell will do, if you're not happy with your solution yet, you have to go along x1 direction and maybe x2 direction to 4 and 5 and create the new position number 4. This is the new acceleration step that connect from the first step of the x1 in each round, in each iterations, with the last step of the last x, maybe we call the xn, something like that. Okay, so the idea is very simple. Try to make the thing go faster, right? The searching may be faster, they believe. So let me remove or clear. So I will not go into the detail for this because it's just very similar to the univariant, except they have the acceleration step. You can self-study, not so difficult. The steepest descent is the way that they do quite different from univariant and Powell because they use the gradient function, the grad of the f of x. to create the direction. They don't go along x1, they don't go along x2. They believe that they need to go along the gradient function. You see in the S equal to gradient, the grad of f of xi. And they believe that this S vector is the best direction. And you multiply with the alpha r, you see. So that this is another idea to define the best direction to go. They don't trust to go along just x1 and x2 or even the acceleration step from Powell. They believe themselves that the steepest the steepest direction or the best direction is the gradient. They define like that. And there's another idea like the parallel tangent, the Newton method. The Newton is solving the problem, right? You see, they just assume that allow my xr present location is define the function f as the quadratic equations. And if I assume my objective function is a quadratic equation, even though in reality, my objective function is another function, is not the quadratic one, they just assume that the function f, the objective function of mine is a quadratic function. And if this assumption is correct, allow the position I'm sitting or the existing position, the present position of my xr, then the best location or the optimum point is defined as the xr plus 1 equal to xr plus, minus Hessian of xr inverse multiplied with the gradient of f of xr like this. This is a Newton. And you see, you need to solve this equation for xr. And the last one is about the optimization. For the optimization, the MATLAB, maybe it's easy for you. This quite old example, so I don't believe it's a good example since the function, maybe 10 years ago, I used this function. So the function, everything have been changed already. Why don't I use the new one for you? Maybe I will introduce you the MATLAB optimization toolbox in a very short time, within 10 minutes. And after that, you can have the question and discussion. Since your friend have some question waiting for me already. Okay, let me try with the MATLAB again. And I will stop my handout here. There's no need to use them anymore. Let's go back to the MATLAB. Yeah, let me clear this. You see on the right-hand side, the workspace. After I'm working on the MATLAB, there's a workspace like this. And this is the kind of the variable on the workspace. If I just type in clear and press enter, they will remove everything. The first thing that I would like you to check after you install the MATLAB in your computer, that is to just type the version. When you type the version, they will tell you about the version that installed in the PC, your PC. And I think the one that I would like you to focus is here. You have to install the optimization toolbox, okay? So that you can have some more function that related with the optimization algorithms. Okay, so you have to tell the MATLAB during the installation that you would like to install also the optimization toolbox. And the one more toolbox that I would like you to do when you will learn about the numerical technique for the differential equation is this one, signal processing toolbox. And maybe partial, maybe don't need. And the symbolic math toolbox. I need optimization, I need signal processing toolbox, and I need a symbolic math toolbox to discuss with you, maybe in the next chapter, okay? Please install at least 3 of these in your MATLAB. And after you install the MATLAB, I think you better focus on the demo. I will tell you. You can type the demo or tour, maybe the same thing. We will open all the demonstration, MATLAB example, or guideline, or something like I don't know. It's an example. It's information for you to study. It's not so difficult. And if you turn on the demo or tour, I think there's an optimization toolbox here, right? On the, you see my cursor over there. I just click on the optimization toolbox. It will show me all the examples that provided by the MATLAB. And I will use this one with you. Okay, this one. The tutorial for optimization toolbox, this one. Just open the tutorial of the optimization toolbox. You will see here, right? That okay, they would like us to, this is an unconstrained optimization problem. I will go very fast with the unconstrained optimization example and constrained optimization example. This is a function, right? X multiplied with the exponential of to the power of minus x squared plus y squared plus x squared plus y squared or over 20. Or it's very difficult function actually, this one. But never mind, they define first here. F is a function of x and y and is equal to x multiplied to the exponential of x and y, like that. Okay, it's very simple. Maybe I just make a copy, Control C, and I will type you here for you in the command toolbox. You see, I just copy from the example, right? And press enter. So you see on the right-hand side of the workspace of mine, I already contain my function f. And the next is they want us to, it's a here window, right? This is a plot surface from x and y from -2 to 2. And they put the contour on as well. So the plotting is quite interesting. You see, there's a surface and in the same time, there's a contour plot in the same figures. Let me try to copy them like this and press enter. I should have the contour plot now. Okay, good. This one, you see, I also obtained the same thing as the example show. This one. And you can rotate in 3 dimensions. You see there's a optimum point is here, right? Close to here. It should be the minimum point, sorry. It's quite the, like you contain the deep valley and the mountain, right? In this function. It's quite difficult function. What the next? The next is you define the functions of x. You see, before we have a function of x and y, but using the optimization, I think they will force you to have only x as the unknown. But in your x, you can have x1, x2, x3, x4, x5. Okay, they don't want to have x, y, z, a, b, c as the unknown, as the variable for the optimization, for the searching. So they want you to using only x, but in the x, you can be a vector that contain many x inside, okay? That's why they have to change from a function f to a function fun. I think it's that's different. Maybe I don't need to copy and to show you one by one. Just explain to this tour, maybe it's faster. And after that, they just, okay, this is the initial position, right? Saying that, oh, I'm sorry, it's too big. Okay, saying that we will start from minus 0.5 and 0. Okay, and then this is the option they put the option equal to option is the optimization function option, saying that I will use the algorithm of function fmin_UC. I will change the algorithm in fmin. This is how to say, this is the main function. The function to minimize the unconstrained, UNC is the unconstrained optimization. And in this function, I will change the default algorithm. I don't know the default algorithm. What is the default algorithm? But you can define any algorithm you prefer. The MATLAB have maybe 10 of algorithms that you can play around. I say the default is a quasi-Newton. Okay, never mind. You can have another option here. If you don't want the quasi-Newton, you prefer a steeper descent, you prefer the Powell technique, something like that, you can define there. Okay, the MATLAB will know that if you call the fmin_UNC, they will use this option for you, this algorithm for you. Iteration means that they will turn on the iteration. So the MATLAB will show the iteration for you. It's better to. Let me try this. Otherwise, you will not feel what's gonna happen. It's not so take so much time, right? Just try the function. So now you see I have a fun function now. And then I tell the MATLAB the starting point. Start from, okay, you see I have x0 now on the right-hand side in the workspace. And then I perform the optimization, but before I better. If I don't turn on, I just call the fmin_UNC and find the optimization. Like this. You see? Oh, okay. They didn't have the option yet. It seems I have to find the option for, I define the option for them. Otherwise, they will. Okay, and then if press enter. Yep. It said that the local minimum file. Okay, so the solution of mine will be contained in the X, and the F valuation is the objective function evaluated at the optimum point. Let me try to show you what is my X. This is a solution. X1 equal to 0.6691 and X2 equal to 0. Or in other words, your objective function is here, right? Minus 6 point something and 0. Could be correct, right? X2 is 0 for sure, right here, the optimum, the minimum point. And X1 direction is minus 0.6. Oh, it's good. Yeah. So it means you obtain the true solution. But if you want to see the iterations, put the output. So our output. They said that I have performed 5 iterations in total, and the step size I did quasi-Newton. Okay, so it's very fast. You see, just press enter, and just a second later you obtain the solution, even though the function is look quite complicated. So the MATLAB is quite powerful, I think. And let you learn yourself. It's not so difficult. If you want to go for the another example, like this is also unconstrained. Let me go to the constraint optimization. Where is it? Okay, this one. You see, there's an example show about the constraint optimization problem as well. And in this example is contained inequality constraint. And this is what the constraint is. Subjected to xy over 2 plus x plus 2 all power 2 plus y minus 2 all power 2 over 2 less than or equal to. Okay, this is one of the examples, and I think it's quite interesting. You see, you have to write down the f function, the g function, and get the solution. 1, 2, 3, 4, 5. Just allow 5 less than 10 sentence. I mean the law. You type very short, you see. You just input 5 row of your MATLAB command and then you obtain the solution. It's very, very fast. Okay, I would like to stop here. This is another example. And you, I think you better can yourself try to get understand about using the MATLAB if you would like to. This is about all about the optimization chapter. And I think next time I will start the numerical technique for the differential equation, right? And that could be the last discussion with you before we have the exam. Okay, so I would like to get the question from you again. Chung Pam Wan Lee. Say, or if some other student have a question, this is the time to ask or discuss. You have a problem about the beta 1 and beta 2, right?
Yeah, I mean, in case if we have a more beta example, if beta 1, beta 2, beta 3, to beta n. In that case, we cannot draw the line or curve the line G1 and G2. And so
you mean that you would like to study more example about beta 1, beta 2, something like this?
No.
I mean to provide more example. Oh.
Yeah, I mean some example have no. We cannot draw the line and the curve for each function because it's maybe each one is two.
This is a question. Right? You are the student who asked this to me, right?
Yeah. When I read this example,
you have another questions. You're not clear, right? You not understand yet. You think?
Yeah, I think delta B1 infer plus than delta F. And I mean if we from above figure, but some line and some curve we cannot draw the line. So
you cannot. You can. So you have to believe the beta, right? That's why when you draw, you'll be able to draw the line. So it's easy to explain you because you can see, right? You can see what is the physical meaning of the beta 1, what is the physical meaning of B1 when it increase or when we decrease or reduce. So in real application, you cannot draw the line. Even the curve, you cannot, right?
Yeah.
The value you obtain from beta, you should know this related to the derivative of objective function f with respect to the bi. And that's why we have learned about this, because in general or in actual application, you cannot draw the line and the curve. So if you look at the beta and lambda, right? The Lagrange multiplier, whether it's a positive or negative. If the beta return me positive number, what does it mean? It means what? It means if I modify my bi to a positive number, not a positive number, increase bi, If I increase BI, my objective function will be also increased. And the rate of the increasement could be depend on the value of the beta itself, right? If you have a very large positive beta and small positive beta, which one is faster, the rate of change? I think the bigger, the larger number will tell you that if you just slightly modify BI, you will, how to say, significantly change of your objective function. Your optimality will change a lot. If you change on the beta, that very large number, for large beta will affect on the objective function very much. This is what I try to say to you. I don't know, you're still confused about this or not. If you're still confused about this one, please write down, okay? Write your questions again to the live group. I will try to address your question. But listen to you, I'm not clearly understand what is your point. But I catch that you trying to say about if we cannot draw the line or we cannot draw the curve, what should we do? Something like this. I'm not so sure whether I understand your question correctly or not.
Yeah.
Okay. Any other questions? No? Okay, good. If you don't have questions, I would like to stop here and hopefully to have a discussion with you on the coming Wednesday morning again about the numerical for the differential equation, okay? I will again use the MATLAB with that chapter. So if some of you not familiar with the MATLAB, please, because in the exam, I believe that I cannot ask you to don't use a MATLAB. So this time, this year, I will ask you to use a MATLAB to solve one problem, real problems, or some complicated problem, but it's not so complicated using the MATLAB. You will finish within just 10 minutes, for example. So please try to make yourself understand the MATLAB and can use them for at least optimization and the differential equations. Okay, this is what I expect from my student using the online learning like this. Well, if you don't have any more questions, I would like to stop here. Okay, and have a good day. See you next Wednesday. Okay, this coming Wednesday, sorry. Goodbye.
Thank you a lot, Ajahn.
Yep. You're welcome. Bye-bye.